Hi there, and thanks for joining us for this webinar on using a 5E instructional model with next generation science standards. My name's Francis Vigent. I'm a former teacher and I am a founder here at KnowAtom. KnowAtom is located just north of Boston in Salem, Massachusetts, and we have been around designing next generation style curriculum for over 10 years. And we work with school districts all across the United States and even internationally to meet the needs of the new standards, but really to help transition from traditional models of instruction to next generation models of instruction and curriculum. So with that in mind, what I'd like to do is give you a couple quick pointers. One, if you're on the live session, you'll be able to ask questions. On your screen, you'll see that there's a question panel. And what you can do is just click into that question panel, drop your question in, and we'll do the best that we can to try and answer as many of those questions as possible. With that said, there's several hundred folks on this webinar, so in order to kind of accommodate everyone, what we'll do is if we can't get to your question live, we will try to follow up with it after the session. You also are welcome to reach out to us after the session. If you would like a recording of this session, a link will be made available to everybody who has joined us for the live session, and that will be on demand, and you can go ahead and view this anytime. So without further ado, let's jump into our discussion here. So our agenda in looking at the 5 E's and how they're applied best to the next generation science standards is take a look at what the 5 E's are, what they represent, thinking about some of the traditional models that are used in the science and engineering classroom and applied to NGSS, things like KWL charts, textbooks, worksheets, and those kind of things. And then how can we make more effective use of the 5 E's under NGSS? We'll look at how the 5 E's are transitioning from what many people are applying sort of linearly and sort of a phased approach to the 5 E's to something that's much more nonlinear, something that is combining different aspects of the 5 E's simultaneously as part of that instructional environment. And then finally, to take a look at, or some pointers for looking at the difference between things that are, quote, aligned versus things that are actually designed for the next generation science standards, because you know, you can go to the National Science Teachers Association, you can go to Better Lesson, you can go to anywhere you want and take a look and find almost infinite number of resources that claim to be aligned, but in fact are not necessarily designed for the new standards, or even if they are, miss the mark in this kind of higher sort of skills-based approach to content and mastery that the NGSS requires. So with that said, let's jump right in here and take a look at the 5 E's themselves. So what are the 5 E's? It's, you know, basically another acronym, except it's hard to say E. It's engage, explore, explain, elaborate, and evaluate. Now, the traditional way of using the 5 E's is in phases, basically engaging first, then exploring, then explaining, elaborating, evaluating, and so on. Well, the issue with this is that the 5 E's are not a linear progression. Engaging is not separate from exploring, and exploring is not separate necessarily from explaining. And part of exploring requires elaborating, and all of these things require engaging. So to think of it in a linear sense like that, or even to have structured a lesson plan in that way, is sort of a false start to begin with. But let's kind of go behind the 5 E's for a second and just think about, you know, what are the 5 E's? And really what they are is about constructivist learning. And so that goes all the way back to Piaget and his idea of constructivism. And what that means is that constructivism is internalizing knowledge through our experiences. And Piaget believed that children would internalize knowledge through experiencing their environment, and through new encounters would either match what they're experiencing to their experience currently, or somehow, or their knowledge base currently, Or what they would do is revise that framework and actually sort of adapt to what they have just encountered. So we'll take a look at that in a little bit further in a second. So kind of, I think, a concrete example of what happens in some of the switches that are happening under next generation science standards are somewhat like this. Imagine you're having coffee with your principal or with your peer, and you know that coffee's hot. It's hot coffee, and you've been told that. Well, the thing is that you can be told that the coffee's hot, but you can also experience that the coffee's hot. You know, kind of burn your tongue on this. And so what kind of happens is that you have, you know, two ways of trying to input this information, right? You have hearing it or being told that the coffee's hot, or you have experiencing it. Now, depending on your understanding of coffee and what it means to be hot or what it means to have hot coffee, you may or may not take what you have heard seriously. It may not really match your experience in the past with things that you've drank. And so when you actually experience that hot coffee, it doesn't fit with your current sort of framework, and so causes you to revise that understanding. Now, the issue here is that you can imagine in the classroom environment that, well, essentially what we're trying to do oftentimes is this sort of struggle. We want students to understand what they're experiencing, so we try to tell them all about it. And so there's sort of a fear about the experience either being lost or being something that's, you know, not valuable, because in the classroom, obviously, we have a safe environment. So, you know, this is a bit of a dramatization with a tongue on fire, right? So we're not putting kids' lives in danger in the classroom. But what we're doing is we're trying to, in essence, prep them for the experience, but it's not really that effective. And yet what we're doing is we're saying, hey, we're trying to make great listeners. Okay, so our focus tends to be making these great listeners. And part of Piaget's idea of constructivism is that students have an understanding of their learning process. And despite all of the focus on hands-on learning and inquiry that has gone mainstream for decades, there's still a very heavy focus on be a good listener. And that's not to say that not listening is necessarily a good thing, but it just means that, you know, our focus needs to not be on creating good listeners, but it needs to be elsewhere in helping students understand the actual learning process. So essentially helping them develop the tools to develop their own knowledge set, to be able to answer questions and to solve problems hands-on instead of sort of pre-teaching and then having this sort of you know, lesson cap and a fun experience hands-on. Okay, and I think sort of a visual representation of that is sort of an everyday experience, right? So if your car was to break down on the side of the road, or a child's car when they're older breaks down on the side of the road, as a good listener, they would maybe go back in their memory and say, gee, has anyone told me about this before? And what can I take from what I've told and use that exactly to solve this problem? And so there becomes a kind of frustration where if I haven't been told the answer, then I don't know the answer, so I can't answer the question, so I become disengaged, okay? And this is oftentimes a point of criticism around standardized testing. Teachers will often say that's not on the test. I need to teach a test. And unfortunately, it's a self-defeating point of view because you cannot tell students every variable that they will encounter in a test any more than you can tell them every variable that they'll encounter in life. And so this model doesn't work. Instead, thinking about developing skills, creating an environment where students can encounter problems and build a framework out of that, internalizing their knowledge through experiencing challenges, and also through students reflecting on the challenges they're experiencing, reflecting on the feedback of their own choices, then what's happening here is that the students get a classroom experience that prepares them for that later challenge, even though we couldn't ever predict exactly what that challenge would be. students have a tool set and also some relevant experience to be able to solve problems and answer questions. So behind Piaget's idea of how students internalize knowledge through experiences is this idea that they have an understanding of their own learning process on some level. Okay, so that's sort of that metacognitive thing that people talk about a lot. And then additionally, and that can be really a kind of personal reflections, intentional personal reflection, think of it that way. And then further, that experience leads to a deeper understanding of what a student knows, or I would say believes as well. So kind of back to this, if I've been told something, that is not the same as having encountered a problem. Okay, when I encounter the coffee, I have a much deeper experience with what it means to be hot and what it means to be coffee, okay, through my own experience with it. It's very different than what I heard, okay, because what I heard, I was matching to what my idea of hot and coffee was. Okay, over here, I actually experience it. Over here, if I'm being told about how to, problems with cars, I have no experience with problems with cars. Okay, but if I actually have an experience with a car and trying to solve problems, now I can apply that, generalize it to an actual situation. So that's what this means, experience leading to a deeper understanding of what a student knows or believes, and trying to internalize that. And there's a lot of really interesting research right now that is coming out of an entirely different area, but really around Alzheimer's and dementia research. And I would recommend a book to you that's actually probably be more of a marketing book that goes through some of this, but it's called The Power of Habit. And The Power of Habit, they talk about how some researchers were encountering how memories were stored in Alzheimer's patients and through routines and habits. So our environment and the experiences and what we encounter in the classroom as students or even as adults are basically key elements in not only understanding and problem solving, but actually storing that information, being able to recall it, and forming the kind of habits that are beneficial for science and engineering, but really for anything. So the mechanisms behind this theory that's underneath the 5 E's is that humans are curious and that humans use patterns of knowledge to remember and to respond to information. There's 2 kinds of mechanisms for this. So when humans, or think of children, when children experience something new, they try to take that new thing and match it to their framework of understanding and assimilate it, okay? Basically attach it to that framework. So in this case, if what I believe is true, I can take that and add it to what I know. Okay, it fits my framework. Another mechanism, though, that fits here is that if something that I encounter does not actually match what I know, then I have to accommodate it. So I have to change my framework in some way. And this is what children do. If they encounter something that, like the hot coffee example, what I thought was hot wasn't really hot. There's actually hotter than I was expecting. So my understanding was false. So what I had to do is I have to actually accommodate or revise my idea of what it means to be hot. Okay, so again, not trying to be really far out there with any of this, but just to try and help you understand sort of the basic mechanisms that these 5 E's are trying to unpack for us. Okay, here's how it applies to the classroom. So in a traditional model of instruction, content flows through a teacher who's supposed to be that content specialist, and they explain and they demonstrate, and a student is expected to take all of that in and be able to repeat it, summarize it, or show it back to the teacher. So that if the 2 match, if what the teacher has given matches what the student has given, that's proficiency. Well, the issue with this is that there's not an experience really involved here. There's not problem solving involved. And so it's really recall. It's lower order thinking. It's remembering, understanding, and applying. And what the next generation science standards are really looking for through those science and engineering practices and the cross-cutting concepts is for students to be able to create, evaluate, and analyze simultaneously. So if students are creating, evaluating, and analyzing simultaneously, they have to remember what they know. They have to try to make sense out of that information, so they have to try to understand or extend their understanding, and they have to try to apply it as they're analyzing, evaluating, and creating. So there's kind of a feedback loop that happens, okay? That is not something that exists in this traditional model, okay? If there is no real challenge involved other than remembering, then there's no opportunity to develop a skill, okay? So skill is where challenge, or rigor is where challenge exceeds skill. And so the rigor here is around memorization. Under NGSS, the rigor is around creating, evaluating, and analyzing problems and questions by using skills and developing the content knowledge that we have. And so that's the challenge for the classroom. The classroom needs to be an environment for the experience to engage in these different ideas. So what does that actually look like in terms of sort of a re-articulated diagram that I showed you a second ago? It looks like this. Students are developing skills and using those skills to develop and use content. Those disciplinary core ideas, that's the content, and to form relationships between different areas of content and its behavior, and that's those cross-cutting concepts. The skills that the students are developing, those are the science and engineering practices. The reason you see the teacher up here is because the teacher's acting as a skillful coach. They're trying to strengthen the connection between the students and their skills and that content. They're trying to create an environment, really curate an environment where the student's skills are nurtured, the supports for those skills are dynamic, they're changing over time. There is a full release of responsibility that's achieved early on in the year. And so the teachers engaging in redirecting and monitoring those students. And the expectations of a student in this environment are different, not recall, but in fact to develop and use the content, to step into the role of scientist and engineer, and to actually engage in risk-taking and problem-solving and trying to explain through investigative phenomena. We'll talk about that a little bit more in a second. So that's why you see the next generation science standards articulated as performance expectations and existing in 3 dimensions. You can't isolate one dimension from another and say, oh, today we're going to develop models and tomorrow we're going to learn about the content. And, at the beginning of the year, we talked about all these cross-cutting concepts. It doesn't work that way, okay? Phenomena is the fabric, is the actual context in which a scientist or engineer develops, and that's the expectation of these new standards, that students engage as scientists and engineers and develop a context in the classroom, okay, develop out their understanding. That's why you have evidence statements with these new next generation science standards. This is the evidence that's observable of a child who has mastered that standard that I just showed you. And it's a very simple standard to be able to develop a model to describe the movement of matter among plants, animals, decomposers, and the environment. Okay, so these are all the different facets that are observable features of student mastery. So it's not something that's just isolated, okay? Bringing this back to the 5 E's, in order to shift from that traditional I-do model to an NGSS model of instruction, it's shifting from I-do to you-do, okay? And at most, we think, being a thought partner as a coach, but never I-do, because the I-do and then we do and then you do really leaves nothing for you to do. It leaves no challenge. It leaves there's nothing. It's chewing on bones at best. Okay, so when you think about that 5E instructional model, just kind of going across here, under an I-do model, you'll hear teachers say, and as a teacher myself, I relate to this, and you can look at lesson plans, go online, and you'll see things, teachers of their own lessons saying, I tell them, I show them, or within a lesson plan, it'll say, tell students, show students. That's the traditional model. Okay, this is where you have to be very sharp intellectually to look at the resources that are out there and really consider whether or not they're designed for NGSS or whether they are essentially the same kit with the same textbook with a new cover and some new buzzwords, okay? Because the thing is that under NGSS, you do is the students reflect or the student questions, okay? Exploring is not I'm giving them or I'm demonstrating, but in fact, students are unpacking a problem. Students are developing a model. Students are gathering data. Explaining is not turn and talk. It's not asking questions like what did or what was. It's not that kind of carousel discussion where we go around and get everybody to kind of give their 2 cents in a quick and brief thing so that we've shared. But in fact, explaining means putting the student in the hot seat intellectually. How have you answered that question? How have you solved the problem? How does evidence support your claim that you've solved that problem? How does your prototype solve the problem? And so this is where we start to get into evidence-based writing in that claim evidence reasoning model, which actually goes beyond that. We have a whole other webinar about that if you can check our resource base. But explaining is not, turn and talk. It is not identifying. It's not giving back the teacher what the teacher gave to the student, but in fact, the student being able to construct a narrative on their own from their own ideas and their own experience, okay? Elaborating is not reading about, watching, introducing a new idea. And again, the I do, so you can picture the teacher reading, putting up a video. So, elaborating is students having to make concept self, concept to concept, concept world connections, and to relate an anchor phenomena to their investigative phenomena. Okay, so basically that anchor phenomena being complex real-world situations that are being investigated in the context of within the classroom, and within an investigation that student or that student team has planned as sort of a way of sort of encountering just a thread of something much more complex. Okay, evaluating is not about giving vocab assessments and keeping journals to grade or making sure you have enough homework checks, but what it's about is evaluating from a higher order thinking standpoint. It's about reflecting on the investigative process that I took as a student or my team chose. How did that impact our results? When we made a prediction, a prediction is just a hypothesis, reflecting on that hypothesis, what do we think was the answer to the question, and how has that changed now as a result of that investigative phenomena? And having reflecting on the larger anchor phenomena context as a result of what has happened and the conclusions that we came to in our investigative process, okay? So these things are not things that exist in isolation again. You don't stop exploring when you're elaborating or explaining. Exploring is actually a method of explaining, and you need to be engaged throughout all of this reflectively and critically. And what's key here is that there are 8 NGSS science and engineering practices, and at a high level. These get unpacked throughout the standards, obviously into much greater detail. But you have to remember that the problem with an I do is that it's the teacher doing it. And oftentimes you say to teachers, are your students planning and carrying out investigations? And they say, yes, I do that. And the reality is it doesn't matter what you do, adult teacher. What matters is what can a student perform independently? What is their skill set, not your skill set? And in fact, your skill set as a teacher needs to be get out of the way and to help support the students in productive struggle through that planning process so that they actually internalize that skill and develop it as a habit when they encounter something that requires investigation, okay, that does not meet their framework of understanding. And this is where it goes back to Piaget's research around that constructivism, okay? So nonetheless, so when you look at these blue words, asking and defining problems, developing models, planning investigations, constructing explanations, engaging in argument from evidence, these are all skills that a student needs to have internalized through that structure that the curriculum has created in the classroom for them to encounter on an everyday basis. Okay, not as a culminating lesson or a cap or so on. So what does that really look like in terms of NGSS? So I'm going to kind of walk you through a process here. So what that looks like is everything starting from an anchor phenomenon. So with KnowAtom, we are phenomena-led instruction, teaching, and learning. And the anchor phenomenon, part of the challenge here, is to engage students in a complex real-world situation that causes them to be dissatisfied in some way with either what they know, what they can explain, or the fact that this phenomena even exists. And so that anchor phenomenon leads to questions and problems. Maybe more questions, maybe more problems, so on. But it's a source of dissatisfaction. And so what happens then is that from, let's say that we have a question. In a scientific context, the question gives rise to a scientific investigation, okay? And that's a scientific process. That's an experience, a thread of the anchor phenomena that a student or a student team can encounter hands-on in front of them, okay? They can actually plan to try and answer that question, to do so hands-on, and to observe the phenomena for themselves, to observe the results of their ideas themselves, and then to form an evidence-based conclusion, okay? In the case of engineering, an anchor phenomenon may give rise to problems that we may want to solve. And that problem would lead us to the engineering design process, which is an experience with investigative phenomena that will, again, yield data that we can use to reflect on whether or not our prototype solution to that problem actually solves the problem and form an evidence-based conclusion on that, okay? Now, all of this that you see here, whether it's in the context of a question or in the context of a problem, what happens in that scientific process or in that engineering process is investigative phenomena, okay? It's observing for myself as a student the results of my ideas basically in real time, okay? Now the thing is that that evidence-based conclusion is a point of reflection back on the anchor phenomena, that larger, more complex situation that we couldn't bottle up necessarily and isolate it. You know, it has more than one variable. It's not something that could be bottled up and brought into the classroom. Okay, so an example of anchor phenomena would be something like flooding in the streets of New York City. There's probably 1,000 reasons that you could have flooding in the streets of New York City. But a question that may come out of that is, how does water percolate through different earth materials? Well, we could use a scientific process to investigate different earth materials and how water passes through them to come to an evidence-based conclusion about the impact of the materials that are found in the streets of New York City. Okay, so that's that point of reflection back on our anchor phenomenon to help try and assuage the dissatisfaction, okay, to inform ourselves about that anchor phenomenon. So that's science. In an engineering context, we may say, well, there's a problem. This problem is that the streets of New York City are flooding. So we may come up with some ideas about how that could be solved. Okay, so maybe it has to do with tidal barriers. So we could design some prototypes, test them, gather the data, form a conclusion based on that data, and reflect back on whether tidal barriers would be a solution to the problem of this, you know, complex situation of flooding in the streets of New York City that we're dissatisfied with. Okay, so that's what this looks like in terms of NGSS. And again, back to the difference between NGSS aligned and NGSS designed curriculum. You know, most curriculum is not designed like this traditionally. It's designed for that traditional model of instruction where, you know, you have your vocab, you have your reading, and then you have some kind of culminating activity. Maybe it's hands-on, maybe it's not, okay? Maybe it's real world, maybe it's not, and so on. The key here is NGSS designed curriculum puts the student in the position of being dissatisfied, encountering the anchor phenomenon, and before they even know anything about science behind or the vocabulary or whatever, they look at that anchor phenomena and they say, I got questions about this, or I have a problem with that. Okay, and that problem or question becomes the entire platform for an investigation, either into potential answers to the question or into potential solutions for the problem and to form conclusions. Okay, and so that's what creates the vacuum for the vocabulary for basically the knowledge, and also it provides the framework for understanding that different elements of that phenomena and performing the expectations of the standards. See, this is the 3 dimensions playing out here, okay? There's a content piece, there's a skills piece, and there is a systems thinking piece that goes on within the scientific process, or if we're trying to answer problems, or sorry, trying to solve problems that's happening within the engineering design process, okay? And I'm not going into that in detail today, either process. They are similar but different, and they are different for big and important reasons. We do have other webinars on that. If you're interested, you can take a look at that under our resources section or reach out to somebody on our team about that. What I want to do, though, is take a step further and say, you know, this is dynamic. This is students as scientists and engineers. This is students developing higher order thinking skills, using higher order thinking skills. And so we need to think about what we're using in the classroom and whether or not it's appropriate under these new standards because they are performance-based, okay? So one question I would throw out to you is, does phenomena-led teaching and learning fit the old KWL chart? You know, is it practical that a student can articulate, especially 30 students or 40 students in a room, articulate what they know? Is that really a useful activity? Do they even know what they want to learn? And how would you even prepare for that anyhow? And then a question also being, how well can we really summarize what we have learned as a group? You know, whether it's even kind of reflecting back on prior lessons, if we haven't encountered the phenomena, especially investigative phenomena, to start with, okay? So what I would suggest to you is that that you should consider replacing the old KWL with a WWH, okay? With a why, what, and how. Here's how that works. So when you think about people starting their classes with KWL, instead, try to start with why. Okay, so if you're looking at an anchor phenomenon, if you are encountering something in a nonfiction text, so in the case of KnowAtom, we use nonfiction text as that anchor, the kind of beginnings of anchor phenomena in visuals or even potentially videos at times. But the purpose of that is to establish a reason to care. Okay, so what we want to do here is connect with what students believe. Okay, what is our reason to care? What is, because that's the purpose. So look at, there's flooding in the streets of New York City. Is there a reason to care about that? What do you believe about flooding in New York City when you look at this anchor phenomena? Okay, next is what? What are the elements in that anchor phenomenon that we could explore? What are the problems or questions that we see with this? Okay, and this is where we get students really dissatisfied. What students, because what we're going to do here is that we are going to take the reasons that we care and the purpose that we see in caring about something like flooding in New York City, and we are going to start to become dissatisfied with what we know. Okay, so we're going to take what we believe and really wonder what's behind that, and what evidence do we have for believing it? So if we say it's because the street is concrete, how do we know that it's because the street is concrete? So is that something we could take a deep dive into, have an investigation about? Okay, so what we're doing is moving from that anchor phenomena towards investigative phenomena. So now what we're going to do is we're going to ask how. You know, how we will explore one of these problems or one of these questions as a student. So, you know, again, that anchor phenomenon has many variables. We, as scientists or as engineers, we can't explore every variable at once. We have to kind of narrow it down to one kind of thing. So now we start thinking about how could we gather evidence to try and solve our dissatisfaction with what we know about how water and concrete interact, or what it means when sea levels rise, okay, or how tidal barriers work. And so what goes from here is where you come back to that original piece that I just showed you a second ago. This is where we come up with our problem or our question that's going to be a focus, how we move from that problem or that question into a scientific or an engineering process, and that's our investigative phenomena, where we gather data or evidence to really dig in and see, you know, this is what we think, this is what we're going to dive into, the concrete and the water. What is it? What is that really in real time? What does that look like in front of us? Okay, this is one of the limitations. I think a lot of people feel like they're being, quote, 21st century. We're 20 years into the 21st century now by having iPads and laptops and so on and so forth. That's part of today's classroom. They try to take that further by oftentimes looking for electronic representations of real-world phenomena. And I have to say, there's a difference between a two-dimensional screen and what a computer programmer says that atoms and molecules can do and how they behave, and how atoms and molecules behave right in front of you in real time. And so what I would encourage you to do is to really consider, as you look at these different solutions that are out there, quote unquote solutions, to consider how that investigative phenomena is authentic and how students, which are at all different developmental levels, especially as you go into elementary and early elementary school, are going to interpret that 2D artistic representation, essentially, against real life phenomena, which are governed by the actual laws of physics in front of them, and how that may constrain sort of the diversity of ideas and thinking in the classroom and opportunities to investigate, because that's key. When you are dealing with some hands-on inquiry that is authentic and it's actually happening in 3 dimensions in real time, what you're dealing with here is something that is infinitely complex and infinitely more authentic. Otherwise, it's constrained essentially as an artist's representation. And that changes in many ways the kind of human error that can occur, if it can occur at all, and sort of the diversity of evidence-based conclusions we could come to, and the kind of the depth of reflection that happens out of that. And also, I think especially at the earliest grade levels, how students personalize that information. I really believe that. But nonetheless, so what's important about this is seeing that as students come to these evidence-based conclusions as a result of the investigative phenomena that they gathered, they use that conclusion, compare it to the different conclusions of other teams in their classroom, and it informs and it changes what they believe and their level of dissatisfaction about some aspect of this larger anchor phenomena. Okay, and that's what Piaget was talking about in terms of assimilation versus accommodation. Because if we are dissatisfied with what we know, we don't have evidence to support what we know, and we're dissatisfied enough to investigate it, that means that we can't assimilate really what we have. We have to investigate it and get more evidence to decide whether we assimilate or to decide whether we need to really revise our thinking. And that's what this is all about. We come to evidence-based conclusions, and that revises our thinking about what we believe and about that anchor phenomenon, helps us get closer, perhaps like in something the case of the flooding in New York City, to a global solution for that challenge. Okay, and that's where the 5E model of NGSS and really this shift from an I do to a you do model and changing of that sort of KWL thinking to something that's more student-centered connects with the standards under what's called the nature of science and engineering. So within the next generation science standards, there's a kind of 4th dimension called the nature of science and engineering, which clearly defines science as knowledge from experimentation. And so when your children are talking about science, they should be talking about knowledge from experimentation. And if they're talking about being scientists, they should be talking about answering questions through experimentation, planning and using experiments that they've planned to gather data to grow their own knowledge, essentially. And similarly, in an engineering context, it's about taking that scientific knowledge and using it to solve problems that are identified. So an engineer identifies and solves problems, okay? And as a student engineer, it's, taking our knowledge of science and identifying and solving problems with it and coming to evidence-based conclusions about prototypes, because that's how engineers go about trying to solve a problem. They create a prototype solution, they test it. That's how they get data to inform themselves about that potential solution. And if it actually solves the problem, it can become technology at that point. So that's why you see technology as the next sort of stop here. And technology enables scientists to ask new and deeper questions, and the cycle sort of feeds itself. And in fact, engineers improve on technology that other engineers create, through the course of time and ideas, but also through the development of new knowledge by scientists. The reason you see math at the center of it is it's a tool for communication and for quantifying observations, analyzing them, evaluating. So it's a key part of both science and engineering. So the reason I'm showing you this is that this is exactly the kind of the brain of the scientist or the engineer. And what I haven't done is broke out what the scientific process looks like or the engineering process looks like. And if you'd like information on that, you're welcome to contact us. That's how our entire curriculum is designed. Students are in the role of scientist and engineer on an everyday basis. They are mastering those processes as tools to be able to answer questions and solve problems, but it has no meaning if at the very base of what you're doing, classrooms are not focusing on the student being the scientist or the student being the engineer and engaging in the nature of science and engineering, because that is the number one reason and that classrooms struggle and why people don't understand the difference between something that's, quote, aligned and something that's actually designed for next generation science standards, is that curriculum translates the next generation science standards into a classroom experience where students can be scientists and engineers and actually gain experience performing the expectations and making the connections on an everyday basis in order to reach mastery so that they can generalize. They have a skill set that they can generalize, but also a knowledge set that they can generalize and apply to, let's say, similar but different questions and problems in new contexts. And that's why oftentimes in open response or constructive response items, even under traditional standardized assessments, that students struggle. Okay, and unfortunately classrooms and schools fail because the focus is, I'll back all the way up over here, the focus is on creating good listeners, and the focus is not on an experience with challenges that drive students to have to create, evaluate, and analyze those challenges, okay? And therefore be able to, master the standard and to intuitively, and this is the key, it's like intuitively as habit, to produce the observable features of mastery because the learning, the skills, and the systems of thinking have been internalized. Okay, so it's much more dynamic, and it is not linear in terms of the curriculum, the way this environment works, and in terms of those 5 E's, the way that they get delivered. Okay, the way that they are sort of applied within a curriculum context. So I'm going to show you here is how KnowAtom sort of articulates this within our curriculum. I'm going to try to buzz through this quickly and take some questions and answers. So if you want to drop those in here, you're welcome to. So with nonfiction reading, what we're doing here is we are sort of starting off an experience with the standards in a lesson, and the lesson takes place over multiple days. Engaging and explaining, engaging with real-world complex anchor phenomenon, okay, through a nonfiction narrative, which then students are trying to explain through connections, okay? So it's that concept to concept, concept to self, concept to world connections with this real world anchor phenomenon. So that's that purpose. Why would anybody care about this? And what that leads us to very quickly is a Socratic dialogue, where you see engaging, explaining, elaborating, evaluating, and exploring happening simultaneously. Okay, so a Socratic dialogue is essentially where, whether it's a teacher or students or a combination of teacher and student, are asking questions that require creating, evaluating, or analyzing in order to respond to those questions. And those questions are focused on the big ideas within that real world anchor phenomenon, which they would have encountered through nonfiction reading, but also through videos, visuals, their own personal experience, okay? And the point here is that those connections then become a point of explanation through that scientific argumentation between students, and also as teachers are helping to coach students to elaborate on their ideas. And the thing is that the role of the teacher changes over time. So at the beginning of the year, with students who have no skill set in relation to higher order questioning, Socratic dialogue, teachers play much more of a coach, asking more questions. What happens is as students learn the skill set to be able to argue scientifically, to ask the questions themselves, that's a skill set that they use that reduces the need or the role of the teacher to be a coach in that area, and then students have built a habit of elaborating, okay? And then further also evaluating their own ideas, but others, okay? So again, kind of playing on the metacognitive and exploring the ideas further, not only in just discussion, but looking at areas where we don't really have the answers and using that as a springboard into planning and carrying out investigations. Okay, so where students plan their own investigations in teams, that's where they are engaging in investigative phenomena. Okay, so they're basically pulling a thread out of that complex real-world anchor phenomena that they can access with the materials and tools available in the classroom to look at some specific aspect of it and to explore it more deeply with their own ideas, and then to reflect on that and try to explain through experimentation and through data what the solution to this specific problem or to the specific question would be. And of course, in that process, this data becomes an opportunity to explain again by using those results to form an evidence-based conclusion. So not only verbal sort of argumentation that's backed up with evidence, but also written argumentation. So this is where that sort of common core science technical writing skills, and there's all kinds of connections here which I don't have time to go into right now, whether it's speaking, listening, communication, reading for understanding, all that sort of stuff is happening in these things that I've thrown out to you here so far. But the key here is that, thinking about scientific argumentation, sharing, forming conclusions sort of as a result of one's own experiment is at one level, but then through comparing results between teams and that authentic release responsibility, again, something you can't get with sort of a canned, 2D kind of thing, or something that's an I do, we do, you do kind of, make by number. There's so many different ways that people kind of unfortunately go wrong with all this stuff, but sharing conclusions for it to be authentic is an opportunity to explain and learn scientific argumentation. And then, of course, debriefing and transitioning is where, again, students are elaborating on their conclusions, making connections from those conclusions back not just to the hypothesis or the investigative context, but also to the anchor context, evaluating each other's ideas, and again, kind of having that scientific discourse, okay? And then through scaffolding, if your curriculum is designed appropriately, you're not teaching rocks and minerals all year, but in fact what you're doing is you are taking an integrated approach. And so when you look at something like earth science or earth and space science, you are scaffolding. So you think about, space, well, we have our home in the solar system. What's unique though about Earth? versus other planets. Earth has, not only water and life and weather patterns that are unique, but some of these different elements provide, so something like the presence of water and temperature, the way that it is here on Earth, provides the opportunity for life. And how is that and why is that? So now we have an interaction between living and non-living, and we can begin talking about the requirements for life and how ecosystems change over time, and how changes in the environment can impact the types of life that is found in different areas at different times, and so on. So you can see, and my point in all of this is that this is an iterative spiral that goes lesson to lesson all year long. And these are habits of mind. So think of the 5 E's as habits of mind. Okay, not to throw a buzzword at you, but think about them as habits of mind. And that the classroom experience and these different stages that I'm talking about here are places where science and engineering practices come together with content. And as students are developing their critical thinking skills, they're actually using them to develop and use that content to answer questions and solve problems as scientists and engineers, and bringing it back to Piaget's original research there is thinking about how the children are actually learning. This is kind of a mechanism for learning, right? What we're doing is we're getting students dissatisfied, we're getting them into a situation where they take their idea and they test it, and then as a result of what they encounter, they either assimilate or they revise, okay? So they either are able to take what they encounter and say, yes, that is confirmed, that confirms my understanding, or in fact, my understanding is in essence false, or my, in essence, understanding is not complete. And so what I have just encountered now augments my understanding and changes it. I've revised it. And so now my understanding as a framework changes, okay? And that's where all of these pieces really intersect. And I'm trying, and again, this is kind of complex stuff. I'm trying not to lose everybody. But so there's a lot of different layers that are coming together. So with the couple minutes that we have left, I'm going to jump into questions here in a second. I want to show you things that are, quote, aligned. This is a lesson plan offline that somebody created for a first grade classroom. And I just want to point out to you that this is not designed for NGSS, even though they're saying that it is. It really misses the mark, okay? And this is a first grade lesson, okay? It's dealing with performance expectation 1 PS4-1. And what I'm circling here is that just some key parts, that this performance expectation expects a student to be able to plan an investigation and to provide evidence that vibrating materials can make sound, and that sound can actually cause materials to vibrate, okay? So that's the expectation of the student. But when you look at the lesson plan, what they've done is they've tried to take the 5 E's and break it into some, again, that old world thinking about 5 E's as phases. And what they're doing is they are structuring engagement around what sounds can we hear at school. And so, recording answers on an anchor chart, reading a book, and so on and so forth, okay? Exploring as being listening for sounds on the chart, explaining as being reporting findings, elaborating as being discussing new words or singing a song a couple of times, that evaluating is keeping the students' journals so that future observations can be made at the end of the unit. But the problem with this is that, and when you look at the materials that are referenced here in more depth, what doesn't happen is a student does not plan their investigation. Okay, it's not their idea that they're conducting the investigation with. They're not actually providing evidence and connecting it to the idea that it's vibrating materials that are making sounds. They're just trying to identify sounds, okay? And that they are not also making the connection that sounds are causing the materials to vibrate, that can happen as well. So what's happened here is something, but it's not really anything relevant to this performance expectation other than it's involving sound. And what is highlighted down here in yellow is what they were identifying as being addressed by this lesson. And again, back to it missing the mark. They were saying that the science and engineering practice of planning and carrying out an investigation is being addressed by this lesson. And in fact, students are neither planning the investigation nor are they carrying out the investigation. There's actually no investigation that goes on here. When you look at journal page 2 and 3, one of them is a song and the other one is just like circling pictures, okay? The other piece that they thought that this was dealing with was cause and effect, mechanisms and explanation. So what that means is that, and this is coming from the standards, cause and effect, mechanism and explanation means that you have a cause, like sound, having an effect, like moving a material, okay? So you could think about, you know, the mechanism being sound, causing movement, or you know, or the explanation for the movement being the sound, okay, and this being sort of a mechanism, sort of the input and output as well. Kind of aspect of this is a cause of sound being movement, and vice versa, okay, cause of movement being sound, and kind of the input and output and how we can explain that mechanism, okay. None of that happens here, and yet you see the 5 E's popping up. Okay, and the thing is that this happens in district-created resources as often as it happens in commercially created resources. Okay, so you have to really, buyer beware. So people are wondering about how does KnowAtom design for NGSS. So I can't cover all the grade levels and screenshots here. So what I'm going to say is you can actually go and download a sample Unit 1 for whatever grade level you're teaching at knowatom.com/curriculum, or you just go to the top of the screen and you can download. It's free. Take a look at it, and that way there it'll be grade specific. And what you'll see, what you download is you'll see a teacher's unit. So that's like essentially teacher binder, and then you'll see a student reading piece, and then you'll have to take a look at what's within the student binder to, and you'll have to look at it very carefully to sort of think through how that experience comes together, because it's going to be explained to you, but it's going to be explained, not in little bullet points the way this is, but really sort of element by element. Okay, so I'll show you though at a high level. This is from KnowAtom. So this is how a student investigation looks at a first grade level in KnowAtom. So you have a question like, does light pass through all materials in the same way? So students come up with a prediction. Light travels through all materials the same way. Light travels through, either travels through a material or it does not. Or light travels through all materials differently, okay? Procedure, shine a light through 3 different materials to see, and see what happens, see if the light travels through, see how the light travels through. And then data that gets collected. And again, remember, first graders, we're talking about really, really little guys. Observations. So for materials that we had available in our class, things like plastic wrap or things like, tin foil or paper, white paper, wax paper, so on and so forth. We can look through, and then students can identify different aspects of what happens to the beam of light as it goes through that material, and then connect that to what scientists would call that phenomena, whether it's to be opaque or transparent or translucent. And you may say, wow, those are tier 3 words for a first grader. But what's interesting is that teaching and learning this way, you have students with a framework and an experience with tier 3 words, and so now they're really able to grab them and retain them and use them. And that's something we hear over and over again. Okay, and then we see, we've been doing this a long time, so this isn't coming from nowhere. And then so on and so forth. So I'm not going to have enough time to get into all of that, but what I had referenced earlier was that idea of, well, I guess one thing to think about is this is vastly different than what you saw here, walking around the school, trying to hear noises, reading a book about noises, and singing a song about noises, and I'm not really sure that there's much else to it, at least in this case, but very, very different. This is student in that traditional model, literally hearing noise, being told about it, and then the expectation being that the students ultimately would be able to tell that information back in connection with sound. With KnowAtom, the difference here is a student, a scientist, making a prediction, which is their own, encountering that phenomena, which is real, trying to understand it, right? And then, which I haven't taken a screenshot of, relate back that prediction to the actual phenomena that was encountered. What I wanted to show you here, though, is how that integrated approach works. So I was mentioning earlier that idea that it's not earth science all year long, whether you're looking at kindergarten to 5th grade or 6th grade to 8th grade, but really an integrated approach so that, again, that framework is dynamic. So we're integrating the ideas of earth, energy, life science, physical science, and engineering and applications of technology. And what's key here is that the standards are being taught in groups, not isolation. That's one of the other problems with this lesson is that you see here that this whole thing is about this one standard. Well, in fact, the standard has a ton of different dimensions, and in fact, it interacts with other standards. So that's how students really master the 3 dimensions and are able to develop those habits to produce evidence of their understanding at a mastery level, is to teach standards in connection with each other. So by grouping them and having, focused standards for mastery, but also introducing future standards and reinforcing past standards. And you can imagine that a student who's tested in 4th grade or 5th grade, they're being tested on all the grade levels prior as well. And, no matter what teachers may think, what some teachers may think about their ability to teach and to know what's on a test, what we know is on the test is the standards. So if we can get students to master the standards, then in fact they have mastered the test. And so the goal here is to address the standards in an integrated way at a grade appropriate level, introducing, mastering, and reinforcing one grade level to the next, so that if a student shows up in your school in grade 4 when they're tested or in grade 5 when they're tested, they have an opportunity to interact with all of the standards content and to connect that to their prior experience and to not have a sort of systemic gap. The other thing that can happen too when you have that, you see this a lot in middle school where people say, oh, earth science is grade 7 or 6. I don't know why it's always grade 6, but anyway. So the thing about this is that what happens if a student wasn't there for grade 6? Okay, what if a student was there but they had some home issues or they were having personal issues or whatever happens? Okay, it's a once and done. What happens if a teacher goes out on maternity leave? That means that when those students from 6th grade, where their teacher was on maternity leave, get to 8th grade, their understanding of rocks and minerals and earth science and everything else is the result of a long-term substitute. There's a lot of reasons not to do things the way that they have been done by some districts, that have produced the issues that the next generation science students are trying to solve. So with that said, I am happy to take some questions. We are a couple minutes over. I apologize for that. This is the link that some folks were looking for. If you'd like to download any samples to look more in depth at what next generation designed curriculum is, really beyond alignment, things that's truly aligned. If you have specific questions, we do have documentation on how KnowAtom in much more depth, deals with the standards and with the 5 E's and everything else. And you're welcome to reach out to Mary Ellen DeLacy, who's a curriculum specialist here at KnowAtom. You can call her at 617-475-3475, extension 2006, or email her at mdelacy@knowatom.com. Okay, and you're also welcome to stay connected to us. We do these types of events as often as we can, and whether or not you are in a position where you're trying to fend for yourself, to try and create your own curriculum, to try and make the best choices for curriculum that you'd purchase. please stay connected. If you are in a situation where you're looking to adopt curriculum, we do have kindergarten through 8th grade that has all been classroom tested. Really, the roots of what we do have been tested for years with hundreds of thousands of students. The way that KnowAtom was able to be next generation designed so quickly is the result of our company being a company of teachers, people who have spent a lot of time in the classroom, science teachers, and also following the next generation science standards through their development process and really looking at those early publications all the way back to 2008, 2009, and developing in the best practices and findings that were published simply because they were great for teaching and learning. And the reason that we at KnowAtom are so excited about science, technology, engineering, and math is not because we think every student should be a scientist or an engineer. We're excited about it because we think that, and we know that when students are challenged to be scientists and engineers, that they are actually developing those critical thinking skills, the creative, evaluative, and analytical thinking skills that are useful for any college or career choice, and that's key. And so that's what opens a world of opportunity to any student, and that's why we really see these next generation science standards as going beyond content. Content's not enough anymore. It's that the development of skills and the ability to develop and use content as being so vital to the classroom experience. So I won't riff anymore. In terms of these questions, I'm going to grab a few. And do my best to answer those here. So some folks have asked for examples of lessons and ideas of how to change or move towards NGSS standards. You're welcome to go on our website. The link is right there at the top. You'll have to type it in. You can't click on it. And hopefully, I hope you're inspired there. You can also take a look at our scaffold summaries, which I had shown previously, those sort of rainbow-colored charts. In terms of other people who have asked about tight budgets, inexpensive ways, love to do more explorations, but there's limited consumables and so on. I think this is a very real problem that a lot of people face. And the real problem is that science has often played third tier to ELA and to math. And the bottom line is that science is a platform, and engineering is also a platform for really deeper ELA and math skills and applied ELA and math skills. So if you want students to be able to do technical writing and communicate with precision, science, what we've talked about today is the context and venue for that, okay? If you have your students getting, talk about ELLs, English language learners, if they're being pulled out for ELA and they're being pulled out for math and you're not pulling them out for science, then you're probably not teaching science, okay? If you have students on IEPs for ELA and for math and there's no mention of science, then you're doing a disservice not only to your performance data, but to your students in terms of their ability to learn science and engineering under these new standards. And the same thing comes to budgeting. If your school's taking that 5% or 15% of their budget and spending it all on ELA and math workbooks and nothing on science, or giving $100 to a teacher to buy whatever they want for that year for science, you're not going to get anywhere. Okay, and unfortunately, under these new standards, what's going to happen is that you're going to see the bottom. It's like you're going to see a new low. That's just how it's going to work, because the thing is downloadable reference resources, reading out of books, learning through physical manipulation in a more play sense, which is really what a lot of hands-on learning boils down to. And I don't mean that as an offense to anybody. You know, again, as a teacher, I'm guilty of this myself at times, but when you don't know any better, or when the standards don't require anything different, how, you know, what is the difference between having students walk around and listen for sounds versus plan an investigation and actually gather data that's relevant to reflecting on an idea? You wouldn't know the difference, but the standards are in a new place. And so when it comes to things like mainstreaming students, the way that IEPs are formed, and the way that budgeting is done, people really need to take a different look at things. And that starts with principals. It goes from there to districts. And teachers need to be truly dissatisfied with taking their own money and their own time and finding materials and trying to make it work. I mean, you know, I'm not sure where else other than education. I mean, imagine going to the hospital and the doctor comes in and says, oh, you know what? I got to go out to my car and get my drugs. I got to go to my car and I got to go get some of those, you know, that gauze I picked up at Walmart. It's ridiculous. But that's the way science has been treated in K-12 for decades. You know, we wouldn't expect hospitals to perform well if the doctor's running out to their car and getting the Walmart gauze. We shouldn't expect classrooms to perform well in science if we're expecting teachers to go out and spend their own money and, you know, kind of patch it together. And then the same thing with the level of, you know, what is expected of that classroom environment. So, you know, principals are really the folks who have to bring that to the district level. Teachers really need to have those conversations among themselves and bring it to the principal level. And, you know, as a profession, we need to move forward and get over some of the way things have been done for years. And that's not true of everybody. I mean, there are certainly districts that take a different approach, but I'm glad that somebody brought that up. In terms of somebody had asked about the lesson that was over here, what might this look like if it was truly aligned? Well, essentially, what it would look like is students considering a real world context where sound is being created by objects, where there's actually a mechanism and an explanation for what's going on, but it's really complex. So it could be something like, you know, a video of fireworks on the 4th of July. It could be something like, you know, a short video of cars being crushed at a junkyard. I mean, there's so many different things that could act as anchor phenomena, but the key here is that there needs to be a transition from a real-world anchor phenomena, which there really isn't one, there's no anchor phenomena here, into students forming those different connections and then moving towards, you know, towards dissatisfaction with the level of connection they have and planning, okay? Planning a way that they can try and answer one of the questions that they have or to try and solve one of the problems that they're observing. And so in this case, it would probably be trying to answer a question, you know, where is that sound coming from? And so now we could actually look at the different materials. So we have that, you know, car being crushed. Well, where's it coming from? Who's making the sound? Is it coming from, you know, the crushing of the material? Like what material specifically? Is it just the two objects coming together? So now we have the foundation for an actual investigation. So, you know, we could bring objects together. We could crinkle things. We could look at different kinds of materials. Okay, what happens when we move them? What kind of sounds are made? Okay, then we could actually go at it the other direction. We could make sounds and see if those sounds can move materials. Okay, and so there a student actually begins exploring and engaging with at an investigative level with the phenomena, and there becomes a platform to explain it, and then through that investigation we can come back as a group and pool our findings and reflect as a group and elaborate even more on what we saw, not only up front and personally in our investigations, but in that anchor phenomena. And, you know, that is what becomes the, you know, platform for evaluating our ideas and each other's findings, human error, and so on. And that is really what's at the root of what they were looking for in terms of planning and carrying out an investigation and looking at the cause and effect mechanisms and all of this. Okay. There's a bunch of other questions. I'm just going to scan down this really quickly and see if I can get a couple more. I will hang on for a couple more minutes. Again, I apologize. There's so many. So in this, there's a question about this particular example of, something that's not aligned. What was the phenomena that was shown to the students? There wasn't one. They were sort of going to be sent out into the hallway to get it. In terms of the one that I showed you from KnowAtom over here, the phenomenon, I don't know off the top of my head. I apologize. There's like 80, 90 units, and each of them have, 3 or 4 lessons in them. So unfortunately, I just don't recall in this case. But if you want to email us, we can find out for you and get back to you on that. In terms of anybody who's looking for recording or certificates of participation, again, you can email Mary Ellen DeLacy down here, and she will get you with that. Just reference the webinar title, the date of your participation, your school and name, and she'll be able to get that to you. If you're looking for a full recording, one will be sent to you typically within 24 to 48 hours. It sort of depends on how long it takes to get that recording turned over. And you're welcome to view that on demand anytime. If you don't get that, feel free to reach back to us, reach back to Mary Ellen, or do a contact us at KnowAtom.com, and we will get that link to you. Keep an eye on your spam or junk mail filters. Unfortunately, when we send links, things happen there. And then other folks have asked, do we have kits with materials available for purchase or rent that go along with the curriculum? And the answer is yes. We don't have them for rent, but we do have them for purchase. And you're welcome to reach out about that. We have every grade from kindergarten through 8th grade. In some settings, communities will use some of our middle school products in high school, believe it or not, simply because they are quite rigorous, and they meet the requirements of certain learning environments. And what I mean by that is oftentimes alternative learning environments, English language learners, and others in adaptive programs is where we are sometimes involved in high school. But typically all of our programming is grade level specific. All of that is there, and we would be happy to have a conversation with you if that's something that's appropriate to you. So with that said, I again appreciate all of the questions. If I didn't get to a question on here, I will do my best to get back to you within the next week or so. Thank you again for your time, and thank you for joining us with this webinar. Please reach out to us, follow us at our blog, knowatom.com/blog, again, free. Follow us on social media, facebook.com/KnowAtom. If you enjoyed the webinar, please, we'd love a 5-star review. If you're a KnowAtom user, please, again, if there's other webinars that you'd like, or even if you're not a KnowAtom user, feel free to reach out anytime and let us know. We're always looking to support our fellow teachers in the field. Have a great day. Thank you again, and bye-bye for now.